So, if we remember the last lecture, what we looked at was nucleophile additions. And we looked at a nucleophile addition that differed from our electrophile addition, because the electrophile addition, again as a reminder, there's an R in there, looked at non-polar pi bonds. And that really meant carbon-carbon, or, sorry, carbon-carbon double bonds, which was our alkenes, usually the primary focus for our electrophile additions, but it can also be applied to alkynes with the triple bond. The nucleophile addition that we looked at changed it up, because instead of reacting nonpolar pi bonds, we look at reacting polar pi bonds. And when we react a polar pi bond, we're looking at that carbonyl as being our polar pi bond. One of the things that it didn't really address, at least to my recollection within Monday's class, is that we really just focused on the carbonyl. Carbonyl isn't officially a functional group, though. What are the functional groups that contain carbonyls? Good. We've got aldehydes. Yeah, there's lots of something else's. Ketones. Right. We also have carboxylic acids.
Yeah.
We also have esters. We also have amides. The amides is a challenging one because that's not what I told you to memorize. Okay, but the amide is there. Other ones that, again, you're not told to memorize. Acyl halides have carbonyls, and anhydrides have carbonyls. And we'll look at examples of those in just a little bit. Okay, but the kind of important piece to address here is that if we go back to that nucleophile addition with the polar pi bond, we're really only talking about aldehydes and ketones. We don't talk about this whole other class, okay, which seems a little bit weird. Okay? To understand why not, we have to double back to our nucleophile addition and address what's going on with aldehydes and ketones. If we're looking at an aldehyde or a ketone, we're looking at carbon on at least one side and then carbon or hydrogen on the other. Okay? When those go through and react with the nucleophile, electrons come in, we break the pi bond, and then that's it. Okay, we neutralize our kind of intermediates after that, and we're just kind of done with that chemical reaction. Okay, if we look at what happens with the new reaction, the nucleophile addition and an elimination, okay, well, that chemistry is still involving a polar pi bond. So if it's still a polar pi bond, there must be something different about the reagent in the nucleophile addition elimination than there is from the nucleophile addition. Okay, and what it ultimately comes down to is it's a polar pi bond with a leaving group. And before we look at what those leaving groups are, that can help us if we go back to looking at our aldehyde versus ketone. Carbon and hydrogen are horrible leaving groups. Okay, since they're bad leaving groups, the reaction stalls effectively after the nucleophile addition and we're done. It can't advance forwards. But if we go through and introduce what the other functional groups, okay, that's this kind of other category that we've got over here. Okay, and in particular, I'm going to pick the acyl chloride or the acyl halide as an example. If we look at how they're different, it's still a polar pi bond, but now we need a leaving group. Okay. And again, out the other end, we probably have some kind of carbon structure that's ultimately not largely affecting our overall chemistry. In the case of the halide, that leaving group becomes any kind of halogen. So in this case, I'm going to call it chlorine, because I keep saying acyl chlorides, just as a reflex. How does this change our overall chemistry? Well, the nucleophile still sees a polar pi bond. So it can still come in and attack our carbonyl and break open that pi bond. What I didn't show in the previous case for the nucleophile additions, at least on this slide, is the product of that. And if we look at the continuation of that product, hopefully what we'll notice is something kind of new or potentially different and interesting about this, particularly since we've prefaced it with how it is different. We said it was different because it had the potential for a leaving group. Chlorine is a pretty good leaving group. It could leave the structure at this point. But if it leaves the structure, it would leave behind a carbocation, a carbon missing electrons. So what happens to help that out? The electrons from the oxygen return. Okay? It's those electrons actually coming back down that helps to force the leaving group out. And this is shown generically. You're going to get variations on this theme of a mechanism depending on your conditions. But our overall result comes out there. So we end up with the carbonyl right back with what we had to begin with. We still have the carbonyl, but instead of having that leaving group or the chlorine on it, we've attached a different nucleophile. Okay? And depending on the identity of what that nucleophile was, we could run more reactions. So if that nucleophile was a carbon nucleophile, what we're ending with is a ketone. Well, ketones, according to the nucleophile addition reaction, can react. So you could get a second reaction happening. So the polar pi bonds with leaving groups oftentimes cycle through multiple reaction cycles or go through multiple reaction cycles because they still end with a polar pi bond. A lot of that depends on the strength of the nucleophile and those typical scenarios. Okay? And we'll look at that a little bit, okay, in just a bit. Okay? If we're going to break down kind of the core functions of our overall mechanism, in that very first step, we have a nucleophile breaking the pi bond. So that would be a nucleophile addition. If we look at the next step, we're making a pi bond. I guess we'll turn this so I can point to it a little better. And the next step, we're using those electrons to come back down to make a pi bond. Because we're making a pi bond, this must be an elimination. Where's my pen? There it is. Well, when we did the elimination, what did we eliminate from the molecule? Whoops, backtrack. That is now looking at this arrow. Okay, what we eliminated from the molecule was a source of electrons. Is a source of electrons a nucleophile or an electrophile? It's a nucleophile, which is why that mechanistic step is a nucleophile elimination, which is why this general class of reagents or reactions is known as nucleophile addition and elimination. Or you'll hear it nucleophile addition elimination. We just drop the and altogether because the addition and elimination stack very quickly on top of each other. Kind of, sort of? So again, what we're trying to do is note the differences in the reaction types and cycles, right, and look at how the functional group changes to match those reaction conditions. Okay, so again, within this new unit, we've got our electrophile addition, which was non-polar pi bonds. We've got our nucleophile addition, which was polar pi bonds. And now we have nucleophile addition and elimination, which is polar pi bonds with leaving groups. Right? So the polar pi bond category ends up splitting into two sections depending on whether or not there was a leaving group potentially possible. Kind of, sort of? Okay. Actually, does this start working again? Yeah, I didn't think that was going to work again. So this kind of goes through and is trying to break down that pattern again. We're now looking at with prettier structures. And in particular, what this is actually a little bit more helpful on is looking for that leaving group. And if we go through and look at the far right, what we're looking at is actual functional group structures. Okay? So at the top we have an acyl chloride, very, very specifically, but if that chlorine was a bromine, it would be an acyl bromide. Okay? You might also hear it referred to as an acid chloride or an acid bromide. Okay? So the class is the acyl or acid halides. When you get specific with what that functional group is or what that leaving group is, that gets a little bit more specific. We move to the next case. Again, what we're trying to do is match the pattern. We've got our core structure, which is the polar pi bond, and the leaving group is connected to it. So if we go to the next one, our core structure is here. This giant piece is the leaving group. Okay, that whole thing is what leaves the structure. Next thing, same deal. There's our leaving group, and leaving group. These are the primary functional groups or structures that you would go through and see when we're talking about nucleophile addition eliminations. Okay, the next one is what's known as an anhydride. Let me actually spell that appropriately. The next one is an ester. You are responsible for esters, I think, right? Is an ester a functional group on that list?
Yes.
Yeah. Then you have amides.
Shouldn't you say this list?
Yeah, that list.
No.
Okay, yeah, I didn't think they were on there. And the ester I'm actually going to tweak a little bit here in a second. And then the last one is a carboxylate. So the 8 is in reference to it being negatively charged. Okay, so you might be like, is that a carboxylic acid? It's not a carboxylic acid. It's the conjugate base of the carboxylic acid. Okay? But you do bring up an interesting point. What about the carboxylic acid? Why is that not on the list? Is it on the list?
Yes.
It is sort of, well, on the list that we've got out here, it is sort of here. Whoops. What does R stand for? Yeah, but what's the identity of the rest of the molecule? And that becomes the challenging question. Typically, R represents anything that doesn't change the functional group chemistry. Right? But there's an alternate definition that it represents carbons or hydrogens. Okay? That's kind of important because if we look at it as a carbon, so this thing is going to split into two categories. If it was connected to a carbon, then the functional group we're looking at is an ester. Okay? If instead it was connected to, whoops, an hydrogen, now we have a carboxylic acid. Okay? So I would argue those are both grouped in the same category, and we'll talk about why that category kind of exists here right about now. These are all listed, you'll note, in kind of a vertical column. Why would they be listed in a vertical column? Why not list them horizontally? It's kind of a hard question. When we think about all the things that we've listed on vertical columns, what do they typically have in common? It's not a guarantee. Typically what we're referring to is energy. These are listed, depending on which perspective you want to go, according to their energy. the acyl chloride or halides are very high energy structures. The carboxylate is very low in energy. Why would the carboxylate be low in energy? Well, before we actually even answer that question, what we should do is take a step back and say, how are all of these things reacting? Well, they're reacting, according to the thing that I just got rid of up here. In that very first step, the nucleophile comes in and attacks the electrophilic carbon. They're all reacting as electrophiles, electron sources, a place for electrons to go. Okay? They want to accept electrons. So in all of these cases, really what we're trying to do is talk about the electrophilic characteristics of the carbonyl carbon. Why would the carboxylate be so low in energy? What could the carboxylate do? Everybody's favorite answer: resonance. The acyl chloride still has electrons, but is chlorine as willing to share those electrons? Nope. Which means that is effectively a non-starter, and we would kind of ballpark estimate and say the acyl halides do not have resonance, whereas the carboxylate does. So that explains the large dramatic difference between those. And what we can go through and do is look at each and every single one of those electrophilic carbons, the blue carbon, and say, well, why? Where would I rank it in terms of its reactivity? And how would we establish that ranking system? Well, we'd start with charge, we'd move to size, electronegativity, resonance, and induction. And what you'll find for all of these is it almost always hinges on resonance, and then a secondary effect, electronegativity. Because you're looking at the ability for that resonance structure to be successful or not. Right? And that resonance contributor has everything to do with the electrons within the leaving group, whether they can donate as well as another atom or not. Okay? You'll note, again, the ester and the carboxylic acid I put on the same row. Why? Well, they have the same chemistry, effectively. The difference between that carbon and that hydrogen, all the way kind of out there, is so kind of insignificant to the overall chemistry between those two when we talk about the chemistry of the electrophilic carbon, that we don't see an effect. And so for all intents and purposes, the carboxylic acid and the ester have identical chemistries. Right? Which is why in lab, to convert the ester into the carboxylic acid, right, we had to do a lot of chemistry. And officially in lab, we didn't convert it into a carboxylic acid, we converted it into a carboxylate. And that was when we made soap. Right? The ester functional group shows up in triglycerides. It's how the fatty acid connects to glycerol. That's an ester. And we add base to cleave that apart to make a carboxylate. Right? And that's why that reaction is successful, is because it's dropping to the carboxylate. It's not forming the carboxylic acid. That can get kind of challenging to look at within the mechanism, because if you draw it out, you would be like, but don't I produce it right away? You do produce it right away, but in an equilibrium reaction that does not favor the formation of the products. You'd have to keep pushing on the mechanism to realize that you have to do an extra step. Okay? Which is kind of beyond the scope of the class, so you don't need to stress a whole lot about that. It's just something to be aware of. And so typically what we would do in a nucleophile addition and elimination section is we would go through each of these individual functional groups, and we would throw all the nucleophiles that we learned with the nucleophile addition chapter now at the nucleophile addition elimination reagents, and we would see what happens. Okay? So it ends up 5 quintupling the amount of reactions that you'd be responsible for. Okay? This is why, again, the primary focus of this class is, do you recognize these differences and can you explain why they're different chemistries? I don't need you to know what a Gilman reagent reacts with. I don't need you to know what a Gilman reagent is. What I want you to be able to do is to look at overarching reactions and say, this is what I would predict to happen, and come up with an explanation for why. Okay? Which can be really, really daunting, and I'll hold off on advancing slides, because you can look at the spider diagrams and go, oh my God, look at all of these reagents. I don't want you to memorize all those reagents. You can do it, and it could absolutely be helpful to you on a test, but it's not going to be helpful in the long term. And in the long term, what I would prefer you to do is to look at the patterns of the reactivities, to be able to predict those patterns and say, this is what I think would happen. You don't necessarily even have to be right within that statement, right? But understanding how things work is much more valuable for you long term than knowing that it works, which seems very counterproductive, right? But the that it works applies to synthetic chemists. None of you are going to be synthetic chemists. So you don't need that it works, you need the how. Okay, what are the patterns and the logic behind how we predict these things to work? Kind of, sort of? Questions about what you see up there?
We don't need to have any of those memorized.
You don't need to tell me what those functional groups are. So if I was going to ask a question about that functional group, you would see me say, how does the acid halide or how does the acid chloride react? Be like, oh, I don't know what an acid chloride is. You don't need to, because I'll have a drawing underneath. It'll say acid chloride. So you don't need to know necessarily that it matches. What you would need to know is what is the chemistry associated with the individual reagents behind it, and be able to predict thereafter. Kind of, sort of?
Yeah.
Which I know is not a happy answer, but it's also not an unhappy answer, I would argue. Right, and I'm hoping I've got a slide here that gives me a little bit of information, sort of to your point. So what I could go through and do, kind of to your point, would be say what's the product that you would expect of this reaction, okay? And the question stem may say, what's the product of the acid chloride shown reacting with sodium borohydride, which is a source of hydride anions? So what does that mean? You have to use some of the language, hydride anions. Well, hydride is H, anion minus. So how would we predict H minus to react with that acid chloride? Well, nucleophile addition. And then if we want to get super, super lazy within it, because we're not looking at mechanisms, elimination. What would we produce? Well, the carbonyl is still there. And instead of it being a chloride, I would have a hydrogen. So I'd have an aldehyde. This is where this unit gets particularly tricky. Do aldehydes react with hydrides? They do. Which means it reacts again. So you end up being kind of responsible for 2 units worth of chemistry, or 2 sets worth of chemistry within one system. Because this is just the nucleophile addition. Do you know how aldehydes react? And then this one is our nucleophile addition and elimination. Okay, So we have to be aware of kind of those contexts within those systems. Does that stack and become more challenging? Yeah. How many questions can I ask like this? Right, and this is something that I keep trying to kind of pull you back to think about this. You're looking at maybe 20 total questions off of this last unit. I have electrophile addition, nucleophile addition elimination, and we haven't even gotten to it yet, electrophilic aromatic substitution. There's 4 new reaction cycles. If we assumed worst case scenario 20 questions, the most I could ask in this particular area would be 5 questions. This is looking at how reagents function. If you trust what I've been saying, I don't care about the reagents. I care, do you understand the reactivities? Do you understand where the reactivity is within the carbonyl? Which means in that 5, maybe you get 2 questions like this. The other 3 are going to push to other content that looks at the larger, broader patterns. Does that kind of make sense? Right. So I think as an example is a better representation to answer your question. Right. So you will see the words, but you will also see drawings to match. Right. And so it's now a question of, can you interpret those drawings based off of that chemistry? This is officially in the play posit, so this reaction will be shown all the way through, and probably in detail, whereas here I just kind of hand waved it. Questions about that? Okay. Looks like you guys are copying, so I'll let you copy that down instead of deleting it all for you. And then we'll backtrack to kind of a useful, or what I would argue is a useful slide for this entire kind of unit. And by unit, I mean day's lecture, this day lecture. So if we pull back to that useful slide, this shows effectively the exact same thing. Okay, but this formats things a little bit differently. One of the things that you'll hopefully note is there's an awful lot of arrows going down. Okay, there are very few arrows that actually work their way up. Okay, and it looks like, I would actually argue, there's really only 2 arrows that work their way up. Maybe this one. Okay. Well, why might that be the case? The acid chloride is the highest energy structure. The carboxylate is the lowest energy structure. How easy is it to go down a ladder? Right? And we're not talking about safe necessarily. How easy is it to get down a ladder? What happens if you just let go? Do you go down the ladder?
No.
No, you don't go down?
Like, what do you mean, like climbing?
Yeah, if I'm in the middle of a ladder and I let go of the ladder, where do I go?
Down.
Down. So if I'm looking at a ladder, going down is really easy. Again, we're ignoring safety. Safety isn't part of this. It's just, where would we naturally go? So when we're looking at the energy of these structures, they naturally flow down very, very, very quickly. How hard is it to get up the ladder? Now you actually have to put in a significant amount of effort. And so if we look at the energy of these systems, you can go anywhere from the top. You can go down one ladder. You could go all the way down to the bottom rung. Okay? That would be painful because that's a large energy drop. Okay? But from the top, you can work your way down to any rung relatively easily. But going up the ladder, significantly harder, and that narrows the field of abilities. Okay? Why does that become important? Well, if it's easy to go down, those are things you don't have to worry about as much if you know the core system. If we know this core block, and I want to go from here to here, what's the difference between those structures? Well, I have this. So what should I react my top structure width to get the product underneath? How about the thing in the red box? Yeah. That's exactly what I do. If I want to move down, come on, eraser. If I want to move down to the ester, what do I need to do? Well, what's the difference between the blue circle and the red circle? We're looking at that OR versus the CL. What do I need to add? I need OR. Really, all you have to do is add the missing piece, and you're done. Moves down the ladder really easily. Going up becomes much, much more challenging. And if we go through and actually look at this, you'll note that the up doesn't happen in all cases. There is no up between the anhydride and the acid chloride. It doesn't exist. The only way we go up is when we target very particular reactions, which means those very particular reactions have very particular chemistry. So to go from the carboxylic acid up to the acid chloride, I need to use SOCl2. If I start here, there is no way for me to go up. What I have to do is go down once, convert across to the carboxylic acid, then I can go up. That's kind of painful, but that's how the overall arching process works. Right? So it's kind of recognizing the downward direction of all of this chemistry, and that really the only way to go up in your system is using SOCl2, which would suggest SOCl2 is a really important reagent to know. And what does it do? It converts the OH into the Cl. It's a phenomenal reagent for it. It's also awful to work with. Byproducts is hydrogen chloride gas, which when you breathe in turns into hydrochloric acid in your lungs. Generally not a good thing. It also produces sulfur dioxide as a gas. The sulfur dioxide, if you've ever smelled rotten eggs, that's sulfur dioxide. Okay? So thionyl chloride, very powerful reagent. It's a bit of a beast to work with. And so what this slide does is kind of summarize your ways to interconvert between each of those individual functional groups. Okay? All of those functional groups can also react with all of those reagents in the last day. So Monday's class, we look at carbon nucleophiles, hydrogen nucleophiles, oxygen nucleophiles. All of them have the ability to do those reactions. Those reactions may or may not fall within this ladder system. Kind of, sort of? Okay. Then it moves into the play posit. The play posit looks at the hydride nucleophiles very, very specifically. I believe there's another play posit that goes through some other reactions, and I wasn't able to find those slides to be able to put them in. Which means content-wise, yeah, you got to look at it, but I'm not going to test on it because I can't find the slides to be able to write questions to test you on it. Okay. But this is going through, again, you can see different pictures of the ladder. This slide adds an extra little bonus to it. What's the bonus? Okay, and before you go, oh, this giant table, ignore the giant table because that's confusing. What's the bonus in the ladder? It's kind of hard to see. They're fainted. They're ghosted. Aldehydes and ketones are added to the ladder here. They're not typically shown in the ladder when you talk about nucleophile addition eliminations because they can't eliminate. But aldehydes and ketones are more active than esters, acids, and amines. They're less active than acid chlorides and our anhydrides. Okay? So if we know that, we can include them in our stair step to help us kind of understand what's going on within those. Okay? And so if we're working with a reagent that reacts with aldehydes, right, if you're forming an aldehyde from the acid chloride, ta-da, you've got the aldehyde you've now got to worry about. And how does it react? So there are next things that can get into here that can become kind of tricky. When this is talking about it, it's introducing these crazy looking reagents. I don't care. I'm not going to ask about them, so don't stress about them. Again, it's something that I think is important. It should be talked about, but I'm not going to test on them. Okay? So those particular reagents target certain functional groups, and they'll produce products that would normally react, but because the reagent has its structure changed a little bit, it prevents those secondary reactions. Okay, so I don't even know how to reference that top one, the lithium aluminum hydride T-butoxide, tri-T-butoxide, very specifically reacts with acid chlorides to make aldehydes. Dibol, okay, the bottom, very specifically reacts with esters to make aldehydes. Okay, so they're neat reagents because someone was able to go through and modify the core functionality of those reagents to target very specifically certain functional groups and to end with functional groups that we would have predicted to continue to react. So they're neat in that respect, but I don't want you memorizing them. You get a little bit of an explanation behind them, but then what we move into is the why do we care about these reactions? Right, this slide did not stepwise through as much as I would have liked, but oh well. What we're seeing over here is an amine functional group followed by a carboxylic acid functional group. And if you put an amine next to a carboxylic acid, what have you formed? An amino acid. Okay? And nearly everybody in this class is moving on through some biochemical chemistry, which is why this class is a prerequisite. Okay? So by putting those functional groups together, we create an amino acid. So we could go through and say, well, why do we care about amino acids? Right? Well, what can amino acids do? Well, I have a polar pi bond in that carboxyl group. I have lone pair electrons on that nitrogen. And if I get a little bit more careful about how I'm showing where these things are located, what I could go through and do, sorry, I gotta draw it all now. And now that I'm drawing it all, I'm pretty sure if I advance the slides, I set it up so I can do this better. You could have the nitrogen act as a nucleophile, attack the carboxyl, break open the pi bond, nucleophile addition. But what do we have in the OH? A potential leaving group. So what can happen? We can reform the pi bond, kick out the leaving group, and what we can now start to form, I should just show it all in black. Is a new connection between these two molecules. And if we look at the beginning and the end, we still have an amine and an acid, but this now wouldn't be a single amino acid. This would be the combination of two. Okay, and they were linked right there through that green bond. Okay, there are some other acid-base steps involved in this, so I am kind of cheating on the chemistry here, but that bond now becomes important and is what's known as an amide bond. Oh, an amide. You mean we're converting the carboxylic acid to the amide, which is straight out of the ladder that we just looked at. So if we look at combining multiple amino acids, if we have more than one connected, what we've now formed is what's known as a protein. And proteins now form a variety of different functions within biochemical systems. So what you would be responsible for in now biochemistry is how do you apply all of that content of amino acids and the amide bonds and those interconversions, and how does that translate into protein structure? Okay. This gets made a little bit more complex and at the same time not as complex as it could be, because you'll note that we have these R groups specified kind of on the side. In biochemistry, our individual amino acids aren't infinite. Okay? In OChem, we can do an infinite number of chemical reactions. We can change all sorts of different structures and make it virtually impossible to memorize anything. But when we move to biochemistry, what we find is amino acids are relatively limited to a few different structures, which kind of makes sense because when you're going to build something, you don't want to have to choose from 5,000 different nails. You want to choose from maybe 2 or 3, okay, depending on what you're trying to do. And so biological systems evolved to use only a certain amount of amino acids. How many amino acids did they evolve to do? 20. There's 20 amino acids. So what you would go through in biochemistry, one of the things you would study would be protein structure. And before you get into protein structure, you have to know amino acid structure, which means you have to be able to look at your amino acids, know those 20 amino acids based off of their structure, their chemistry, and then if we realize a protein isn't made up of 2 or 3 amino acids, it's made up of thousands of amino acids, we want a shorthand so we don't have to draw the entire structure. What are the codes that we would assign to each of those amino acid structures? Right? This slide does that, or this image does that. You've got the structure provided, the name arginine, the 3-letter code ARG, and the 1-letter code R. In biochem, you're responsible for being able to look at any one of those to know what all the others mean. Okay? But now you have to do it for 20 amino acids. Okay? You'll note that there's even more information encoded within this, because not all amino acids are grouped as one category. We've got this kind of green category up here. We've got what one might call an orange category. Yellow's not going to show up, but I'm going to do it anyway. A yellow category. And then a red category. What are those categories in reference to? What they're talking about is the chemistry of the side chain. Right? And I know it's really, really small. Right? It's not easy to see, but this is where you could go back and you could blow up the image. You could find better images online if you wanted. Okay? I don't want you to memorize any of the amino acids for me. What I want you to know is that nucleophile addition elimination reactions are the fundamental building block behind proteins. And they function exactly as we've shown here. Okay? The next fun piece that you'll typically see show up within proteins, or a couple things, is that one of the common things that you're asked to go through and do is that for an individual amino acid sequence, you'd be responsible for knowing that S is serine, C is, I don't know how to spell it, we're just going to say it's cysteine, A is one I always get wrong, alanine, R is arginine, right? Y is tyrosine. Well, that's not that bad. Oops, and serine I didn't write all the way out. I just did the 3-letter code. Okay? But then the next thing we have to acknowledge when we're dealing with biochemistry is what happens if the pH changes, if it becomes more acidic or basic. Okay, well, if it's a more acidic environment, we start to protonate things. If it's a more basic environment, we start to deprotonate things, which means that's going to change the charge on an individual protein. Why does that matter? Well, if the charge is different, I can separate it away from other amino acids and other trash particles that I don't care about. So what you would then have to be able to go through and do is say that serine, and I don't have them memorized, serine has an OH as an R group, and it's polar and it's uncharged, which means it's not going to react. Okay, so it has 0 charge contribution. Cysteine. Okay, where is cysteine? There's cysteine. Okay, a special case with an SH. That SH, I think it's a bit dodgy, and you might have to worry about that one as far as its acidity. Okay, so how would you know acidity? Well, how do we define acidity in chemistry? So we can look at the general just definition, if it's donating protons. Okay? And in chemistry or OChem, it was nice because we could pick a base and say, should it donate or not donate protons? Biochemistry is limited because I can't throw any base at a protein. I have to pick very specific bases. I have to pick bases that are biologically relevant, which means I can only kind of look at what I would argue are weaker bases, even though hydroxide is still in there. Okay? So in that case, I don't want to rank based off of charge, size, electronegativity. I want to know definitively whether it's reactive or not. When it says uncharged, that helps us out. It says there's no charge associated with it. If we're looking at special cases, well, what do special cases mean? That means it might become charged. How would we decide that? We would have to look up the pKa. So one of the extra things that you typically have to memorize, okay, when it comes to a test on protein structure is the pKa for your amino acids. Because that pKa, depending on the pH, is going to change the charge on the structure. So what you could be asked is, what's the charge on scary at pH 3? To answer that question, you would have to know all of those codes, their individual pKa's. Alanine is going to come in as a 0. I know that one. Arginine comes in with some kind of pKa. It says charged side chain, so we're going to have to worry about that one. Tyrosine, I think, comes in as uncharged, but I'd have to look that one up. That might actually have a pKa that's valid. And what you would then go through and do is compare the pKa to the pH and decide whether it was protonated or deprotonated within it. That should sound vaguely familiar, because when did we do that? Unit 2, when we talked about acid-base reactions. So you end up going through that whole process again. So lots of secondary information has to be encoded, and you're responsible for all of that. Yay, science. Okay? Good news, you're only confined to, or you're restricted to those 20 systems. Okay, those 20 amino acids. And even within those, only some of them have pKa's that you need to worry about. So as long as you memorize the ones that have relevant pKa's, you can ignore the rest as far as their pKa's. And all you need to know is their 3-letter code and their 1-letter code. Kind of, sort of? Okay. Said proteins have thousands of amino acids within them. Okay? So what happens to the structure of a molecule that has thousands of atoms in it? Is the structure going to be a little bit different than just a small structure? Yeah? How? Why does that larger matter?
Hold the charge better.
So there could be differences in charges showing up. If we look at an individual person, okay, tons of movement, right? But if we held hands and became linked to each other, does that change how we interact with our environment? Are we going to be able to move as much? No, that's going to change. Would each of us be able to interact with the environment in the same way? So if we linked it, me, Annie, Kimball, Annie, you're going to have a hard time interacting with the world because you're stuck between us. Okay? So those secondary interactions could cause effects. If we added even more people into this, okay, let's say we threw Lindsay on at the end of the chain. Well, you're partners with Lindsay, so when we get to lab, what's going to happen? You need to work with Lindsay. So you're going to have to bend the chain so that you and Lindsay can work with each other, right? And so what's going to start to happen is your structure is going to change and adopt conformations to minimize that charge. Right? And so what biochemists or chemists or biologists went through and did is that they now went through, see, I told you I did the second structure. I didn't have to draw it again. What they went through and did is started to now classify what we're talking about within that structure. And so the first thing that we would see, that orange color is a little bit weird, but you can kind of see it. Primary structure is just the sequence of amino acids. Okay? They did this one a little bit goofy. It's a little bit fancier than I wanted. Because what we would be talking about typically is we would say met, pH, asp, ala. You guys get the idea? So it's just the sequence of the amino acids. That's what we would classify as primary structure. Okay? But then, depending on the interactions between those amino acids, we may see that asp wants to come back and talk to methionine. That's now going to change the structure. And if it changes and mutates the structure in a way that is repeatable and visible across multiple different proteins, what we can then encounter what's known as secondary structure. And in secondary structure, what we're noticing is that it's not just the straight chain, but how did the structure fold? And if it folds in ways where you get lines kind of stacking with each other, we call those sheets or beta sheets. If it folds in a way where we get corkscrews, we'll refer to that as a helix, similar to DNA. Okay? And what we can find is that there's particular amino acid sequences that force either of those protein structures. Okay? So that's our secondary structure. But then those secondary structures can start to talk to each other. And if the secondary structures start to talk to each other, we now get tertiary structure. So how does the beta sheet, notice these blue lines, interact with the alpha coil or the alpha helix? That's now a tertiary structure. But what do proteins interact with? They interact with DNA. That's how we change our DNA and get our DNA encoded or decoded. Okay? And what that now starts to build is what's known as quaternary structure, where you're looking at now super complexes. When I take a whole bunch of this tertiary structure, I can link multiple of them together, and that's now creating a quaternary structure. So we can get progressively larger and larger structures coming out of this to represent an individual protein or enzyme and its function and how it relates to the world. Kind of make sense? Okay. Where organic chemistry sits is typically all the way up there in that structure. Okay, and even then, we're probably talking about the little bit individual connections in those spaces, those amide bonds. And very quickly, what biochem does is build up to larger structures. Those larger structures are built upon the smaller bonds being studied within organic chemistry that then scaffold upwards. Which is why when you look up a protein structure, rarely do you see primary structure. Usually what you're going to end up seeing would be your tertiary or your quaternary structures as your representations for proteins. Because there's just so many atoms within those, it doesn't make sense to convolute it with all of the individual amino acids and all of their individual structures. Kind of, sort of? Okay. When we talk about what I wanted to get through today, I'm pretty sure that was it. Yep. So, what do you all want to do? Should we look at some questions from the practice questions, or should we just continue through into the electrophile aromatic substitution stuff so that that can be done, and then next week is all just study and running questions? What do you guys think?
Sometimes I guess if you want the others to miss out on the information.
Lectures recorded.
It's true.
So theoretically, all the people that are missing class are missing it with the understanding that they're going to go back and watch these lectures. So, to me, I don't care.
Question?
You want questions? Yeah, we can do questions. Let me go ahead and pause for a second. Okay, so the questions. Which of the following molecules would be unlikely to undergo a nucleophilic addition reaction? So what does it mean to do a nucleophilic addition reaction?
So we break the pi bond.
Okay, so we need some kind of pi bond, so I'll just draw two lines for the moment. Okay, we don't know necessarily what these question marks are. Well, it's organic chemistry, so we'll go ahead and say one of them is a carbon. But we don't know what the question mark is, because that question mark could be a carbon, oxygen, nitrogen. Based off the answer choices, those are our possibilities. Okay, so if we're doing addition, we know we have to have a pi bond. What's the next piece of information that the question is giving us? Must be a nucleophilic addition. So noting addition, pi bond, phenomenal, great. We've got our example, but we also know it must be reacting with a nucleophile. What's the characteristic of a nucleophile?
They missing electron. Oh no, they
Nucleophiles supply electrons.
yeah.
Okay, so that thing needs to supply electrons either to the purple, or sorry, either to, we'll color code a little bit better. It either needs to supply electrons to the blue or supply electrons to the green. Okay? If we go through and look at our answer choices, this is where we could start to just go through and look at, evaluate answer choices to say which one of these things makes the most sense. Okay? But I would argue we don't even need to do that. If it's a nucleophile, it needs to supply electrons to what? What would an electrophile look like? Electrons to a positive. Could we see a carbon be positive? Yeah. Okay, could we see a question mark be positive? That's a really hard question to answer because we don't know what the question mark is. But a carbon could be positive. How does it become positive? True. So we'll cheat and say, oh, carbocation. Do any of our answers have a carbocation? No. So take a step back away from that. How does a carbon become positive?
Break the bond. Give away the electrons.
Something must be taking the electrons away from the carbon. Okay, so if I know something must be taking electrons away from that carbon, does that give me any information about what blue should be? Said another way, since I know that question mark must take electrons away from carbon, if I want the carbon to be positive, I know something about blue. What do I know about blue?
More electronegative.
Bingo. This has to have a higher electronegativity. Okay? With that information, I could now go back and look at the patterns that I've got. There's a pi bond, so that fits. Pi bond fits. Pi bond fits. Pi bond fits. Okay, that's obnoxious. All of them have pi bonds. Okay, so what it's now tipping on is what's that question mark associated with this. Okay, and that's dictated based off the nucleophile. Okay, that nucleophile is that question mark must have a high electronegativity. Is oxygen a higher electronegativity than carbon? Yes. Is nitrogen higher electronegativity than carbon? Let's skip to E. E has the nitrogen, right? So what does that mean? A, B, C, and E all fit nucleophile addition. So what's the answer?
Oh, D.
Okay, what's the O? Yes, that's exactly right. Kimball saw it, but what's the O, Annie?
Because of the question, unlikely.
Yeah. It says unlikely. Okay, so let's lean into D a little bit harder. What's the other atom other than our green carbon in D? What's the blue atom?
Carbon.
Carbon. What's the difference in electronegativity between carbon and carbon? There is none, which means neither of them are positive, which means neither of them will react with the nucleophile. Okay? And the reactivity of the alkene is now that I have pi electrons. The alkene will now act as the nucleophile, which means D will do addition reactions, but not reacting with nucleophiles, reacting with electrophiles. Does that make sense? So if we parse together the language that I've been asking you to go through and do to know those definitions, you can now apply those definitions and build up. This is a lovely question that goes through and covers kind of those fundamental core chemistries without having to dig into the reagents, but it's asking you to think about the chemistry associated with each of those functional groups. This is a good question. This is a very likely question to see on an exam. Does that make sense? We good with that one? Are you guys writing stuff?
No, I'm good.
Kind of.
Okay,
And
I'll just pause. This, I would argue, is now veering very heavily into do you know the reagents? Okay, so this is a question type that I'm less of a fan of including on the final. Okay, I don't like this question because it requires that you've memorized the reagent. Okay, that said, I've now provided it as practice. Theoretically, you should know this one. So if you're going through the practice and you compare that to all of the reagent list and you're like, well, I didn't see this reagent in the practice, I'm probably not going to ask about it. Because there's a lot of reagents there to cover. It doesn't make sense to kind of overlap those. Here, I could make the argument that I gave you the practice to look at it and think about it, therefore, I can ask this question on an exam. Or a question like it. Does that make sense? Okay. So just giving you a little bit of my mindset behind how we would approach it. Did we solve this one in class already too?
what one?
This last one? The one we just did?
I don't think so.
Weird.
I think-
Because we did this one
Yeah.
and we did this one. Did we? Oh, maybe we didn't do this one.
We did.
No, we did.
Could you go back to 97? I don't see that creation. Oh, just A2.
So, and this is where you got to be careful. It's not just H2. It is H2, but it's also with Lindlar's catalyst. And Lindlar's catalyst is in the list. I can pull up, you want me to pull up the slide to show you where it is? Yeah. It is slide 3.
Okay, sorry.
No. And again, there's so many reagents. We talk about organics and we barely scratch the surface of the reagents that get used. So again, my hope is that you aren't memorizing reagents. That's fine, you can do it. But my hope is that you're picking up the broader picture of what's going on behind it. Do I have to kind of show these reagents? Yeah. Some of this is just that I have these readily available so I can show these. But they are shown in other classes that I've been a part of. Oops, nope. Did that one. Seriously, you're not gonna load? Okay, let's go ahead and pause the recording while we. Okay. So this can be done through memorization of reagents. I would argue it can also be navigated based off of having an understanding of the chemistry. There's a little bit of complexity here, so I'm going to sidestep that by kind of talking through the simple version of this. So, what chemistry do you see? Electrophile addition, that, I mean, just jumping light years ahead of my question, but yeah, okay. I would argue what you should see would be you have nonpolar pi bonds. Nonpolar pi bonds means electrophile addition, okay, which means you're somehow having the bromine come in and react with the pi bond, okay. Where would you expect the bromines to appear?
To attack the carbon.
Which carbon?
The carbon have more stable.
Okay, so we're going to walk through your language, which is fine. But I think what you're thinking through, and I would actually argue is nicer, because what you're walking through is looking at kind of the core chemistry behind it. And then we'd have a new bond to a bromine. What would happen to the green carbon? Because if the pi bond reacts to form a bond with the bromine, we'll form a bond between the blue carbon and bromine. But those electrons in that pi bond were shared between the green carbon and the blue carbon. They are no longer shared between the green carbon and the blue carbon, which means the green carbon is positive. It has lost electrons. That was originally Br2. And if our electrons came out to share with that bromine, we also have Br minus chilling around. Where would we expect the Br minus to go?
Go to the green one.
Go to the green one. So if we look at our prospects, what we're looking at is the bromines going one to each carbon. Okay? We only predicted reacting one pi bond, except do we have another pi bond? Yeah, which means
2 more.
I should add 2 more bromines. So if I'm looking at a product what I would hope to see, green, blue, I'd have a bromine, a bromine, a bromine, and a bromine. Okay, so I would expect bromines at both carbons. Do I see that?
Is that all?
We see a lot of this stuff. Oh, there's a bunch of things about enantiomers. Do you need to worry about enantiomers? Why not? Couple pair. Why is there no stereochemistry?
No chiral centers?
Yeah, there's no chiral centers in our product. Okay, since you put all the bromines on those individual positions. I think this question has the potential to be a little bit more complicated. This would be the answer I would expect you to give. Okay, so that extra complication isn't something I'm going to talk through, but if you talk to a tutor, they might make it more complicated. What I would do is mitigate that issue, and the way that I would mitigate that issue as a potential extra complication seems a little bit strange, but all I would end up doing would be adding an extra carbon. So you wouldn't have to worry about it. Okay? And then that extra carbon would be added in all of those individual structures. So I would modify the question to remove that secondary problem, which may or may not actually be a problem with this. I'd have to look at it a little bit closer. I think it would be a problem. So you don't need to worry about that problem, but it could easily be an issue that could pop up, particularly if you're talking with an expert. Okay? Kind of makes sense? So within that, did we actually know what the reagent did? Or did we just follow the chemistry that we've been taught? Okay, and it's up to you how you decide. I would argue you follow the chemistry all the way through. You said it's an electrophile addition. Admittedly, I don't know why you said an electrophile addition. So to me, I shifted back and said there's a polar pi bond or a non-polar pi bonds. Non-polar pi bonds react as nucleophiles. They have to react with electrophiles. We established the bromine. We drew out those pieces. We started connecting the things. We recognized there's two pi bonds. We did the reaction again. Okay? So what we were following is positives and negatives all the way through that reaction without actually drawing a real mechanism. Because the mechanism we've drawn is actually horrendously wrong. Okay? But we don't need the specifics behind it in this particular case. We can follow the chemistry of what we've been taught to navigate to that answer. Kind of make sense? With that, we're done, so I'm going to go ahead and stop the recording.